So yesterday we went over section. It was 2.2. Yesterday. Um, yeah, 2.2, and we want to go over some of the discussion problems. So let's see. So the assignment from 2.2 is 38 and 52. All right, so 6 to 24, every third problem. So in 6 to 24, you're given a variety of functions to sketch their graphs. And a lot of time they ask you for, like, make a table of values and then, use that to help you draw the graph. That's not always the best approach. Um, well, it's always like not the best approach actually. Uh, but sometimes you know what the better approach is. Is to know what standard functions, what their graphs look like, or at least have some idea what they look like, and then there'll be variations on what those standard functions look like, which is something that is talked about more and more as time goes on. So far, what have we discussed? We've discussed lines, and we've discussed parabolas, or sorry, the basic parabola, and circles. Um, and then we'll discuss some more later on in the semester. But in number 6, they give you this function fx equal to 4 minus 2x. Sketch the graph. Y equals f of x. So when you don't know what the function is, you just write it like that. In this case, we're talking about y equals 4 minus 2x. So in sort of slope-intercept form, minus 2x plus 4. Well, what is this? This is the line of slope negative 2 with y-intercept 4. So we know all about that kind of thing already. Right? Here's the x-axis, y-axis. Here's the 4. And then, what's the x-intercept? 2 lines is enough to give you the graph. The x-intercept, setting this y equal to 0. So if y is equal to 0, then 0 is minus 2x plus 4, so x is equal to positive 2. So positive 2 would be about there. So now we're talking about the line that goes through these 2 points on the x and y axes. Right, so that line there. Right, we're not using a table of values. I really haven't even gone over what a table of values is, although it's basically just a bunch of points that go through the curve, and then you connect them in some way. But that doesn't tell you the full story. It misses significant parts of the story. Number 9, fx equal to minus x squared. So sketch the graph. Y equals f of x, which in this case is y equal to minus x squared. Okay, well, we've talked about the standard parabola. Okay, the standard parabola looks like this. So it goes through the origin and then has two sides like so that are mirror images of each other. So I will actually take that picture, copy it, and then flip it, and here it is. So there is a picture of the standard parabola y equals x squared. So this is x, that's y, and then we label that y equals x squared. Oh yeah, and in this one you would label it y equals minus 2x plus 4. Now, of course, that's not what we want. We want the graph y equals minus x squared. But what would be the relationship between this graph, y equals x squared, and the graph y equals minus x squared? What is the relationship between this, y equals x squared, and y equals negative x squared? Well, keeping the same x coordinates, we're going to take the y coordinate and negate it, which will do what to this, do you think?
Flip it.
Flip it upside down. Make them negative, right? Copy, paste. So actually, let me make this one smaller. Just sort of store it away here. So now, with this picture, I'm just going to copy the parabola. Oops. Come on. I'll just take that, just erase it. So here it is. So for the same x coordinate, you get the y coordinate that is negative. So here's the x-axis and here's the y-axis, the negative part of it, positive part's up here, and then this is the graph y equals negative x squared. Now, why would a table of values sort of fail to capture what's really going on? I mean, suppose I was to make a table of values and try connecting up those values into some, coherent type of curve. What would go wrong? Or what could go wrong? Right, I mean, if I was to make a table of values, so you take a bunch of values for x. So we'll take 6, 7, 8, 9. So then this is minus 36. This is minus 49. This is minus 64. This is minus 81. So if I'm going to draw that, I've got all these points, right? 6, 7, 8, 9, all the way down here. They're way down here. So that's the graph. You see my point? My point is you could pick all the points that are not showing what's really going on, where the interesting stuff in that function is happening. You pick 4 points. Well, I mean, they could be 4 points that are just sort of unremarkable. I mean, maybe I pick these, well, not on that curve, but on this one, maybe I pick these 4 points. And I plot those points. I mean, it's not going to indicate what the shape of that curve is supposed to be. Even if you pick like 4 points right here, like 1, 2, 3, 4, or something like that, it still doesn't. Right? The correct approach, or the better approach, much better approach, is again what I said, is to know what standard functions look like. So y equals x squared looks like that. And then variations of the curve will be obtained from this, via various tricks that we'll talk about. In particular, we'll talk about quadratic functions. Fx equals ax squared plus bx plus c. They all look like the parabola, just in some kinds of variations of the parabola. Okay. So it was 9. Number 12, x squared plus 2x plus 1. X squared plus 2x plus 1. Okay, so sketch the graph again. So I don't really like any of these problems because we have not really discussed how we're supposed to solve them, and I'm certainly not going to ask you about them on the exam. So this is y equals x plus 1 squared. So again, it's a variation on this. So this is x squared. What is y equals x plus 1 squared going to look like, do you think? Relative to this one, what's it going to look like? Where's that bottoming out going to happen? Right. The bottoming out here happens at 0, right? You pick x equal to 0. You pick x equal to 0, and you get y equal to 0. So the bottom out happens here. So with this one, where does it bottom out? At what?
1.
At, not 1, actually. X equal to, not 1, but what? Right, 1 plus 1 is 2, not 0. When is the x plus 1 equal to 0? At x equal to
Negative 1.
negative 1, right? So, boom, there it is. It just takes this graph, y equals x squared, and shifts it to the left one spot. And the red one is y equals x plus 1 squared. If you want to shift it to the right, it's y equals x minus 1 squared. So, I mean, it's not, it's kind of the opposite of what you would think, this shifting to the left and to the right. 12, 15. I'm not going to do 15. 18. Same. 21 and 24. So, I mean, 24 we can do. That's an interesting case. Oh, is that one I asked you to hand in? It's not, is it? No, 38 and 52. So here we've got h of x equal to absolute value of x plus 1. How is the absolute value of x plus 1 calculated? Right? Well, the absolute value of x plus 1 is equal to x plus 1 itself, as long as it's positive. So when is x plus 1 positive? If x is what? When is x plus 1 positive? Right, when x is bigger than or equal to negative 1. And it's equal to the negative of x plus 1 if x plus 1 is negative. That's if x is less than negative 1. So it becomes a piecewise function, right, which we spoke about yesterday, and which I'll do a couple more examples in a moment. But here, the line y equals x plus 1, we're going to be making from negative 1 forward. So at x equal to negative 1, we're at 0. So this is x equal to negative 1, y equal to 0. And then we have a line of slope 1 extending from that. So slope 1 is 45 degrees, where the rise and the run are equal. And then before x equal to negative 1, well, at x equal to negative 1 itself, at x equal to negative 1 itself, this is again 0. And then we have a line of slope negative 1 coming into that. So that's the graph y equals x plus 1. Absolute values can be thought of as a piecewise function with two pieces. Let's look at a few more of those. So the ones that were assigned, 33 to 41, odd. So 33 to 41, well, how about 33? So fx is equal to 2, or 0 if x is less than 2. And it's equal to 1 if x is bigger than or equal to 2. Right? Well, at 2, where the switch occurs from this piece to that piece, right, so say the 2 is here, for x is bigger than or equal to 2, f of x is equal to 1. So here's the point 2, 1. And if every point after that, for every x value after that, the value of the function is 2, then we get a horizontal line like that. And then before 2, we have f of x is equal to 0, which is on the y-axis. So we get that the function has value 0, which basically puts the graph on the x-axis, like that, with an open dot at the 0 and a closed dot at the 2, when x is, with an open dot at the 0 and the closed dot at the 1 for x equal to 2, because the value of the function f of x is 1 when x is bigger than or equal to 2. Right? So let's look at that a little bit more. Pick a value x greater than 2. Say x equal to 6 or something like that. So x equal to 6 would be out here. Right? So we go straight up, or we go vertically up or down to the graph. And then we go horizontally to the y-axis, and that's the y value. So at x equal to 6, we get y equal to 1. At x equal to 7, we get y equal to 1. At x equal to 8, we get y equal to 1. At x equal to 8.1, we get y equal to 1. At x equal to 2, we get y equal to 1. And then for values less than x equal to 2, like at x equal to 1, we get y equal to 0. At x equal to 0, we get y equal to 0. At x equal to negative 1, y equal to 0. At x equal to negative 1.5, y is equal to 0. So on and so forth. So we have these horizontal lines before and after x equal to 2. So we can label this y equals f of x. All right, so here we write y equals f of x because we don't want to label the graph with this big clunky thing. So that's 33, 35, 35. Let's do 35. So f of x is equal to 3 and x minus 1. Switching at 2. All right, sketch the graph. Y equals f of x. And by the way, in all of these examples that we're doing here, in 33 through 46, well, not in all of them. In most of the examples, 33 through 46, each piece of these piecewise functions is a line. Right? So we're able to graph those because we know what lines look like. The only other thing there are in a few of the problems, the last 3, well, in the last 4 of them, there's some parabolas. But we should be okay with parabolas as well. And basic variations thereof. So let's take a look at this one. Again, we have a switch in pieces at x equal to 2. So x equal to 2 is here. All right. So if x is less than 2, if x is less than 2, then f of x is always equal to 3. So 3 is about there on the y-axis. So if x is less than 2, y is 3. So it's another one of these horizontal lines. And where does the horizontal line stop?
Positive 2.
At positive 2 with a, what kind of dot? Open dot? Open dot, right. All right, so now for x equal to 2 and going forward, we have this line of slope 1. So at x equal to 2 itself, what point are we at? Well, 2 minus 1 is 1. So right about there. So that's the point 2, comma 1. And then after that, we have a line of slope 1 going forward. Slope 1, again, is a slope of 45 degrees. Now, normally you would need like a second point to graph the line like really accurately. But this will be fine. There's just one point and then a slope of 1. Well, that's 45 degrees. So it looks something like that. If you want, this is point 2, that's point 1, so point 3 would be here, something. Point 4 is here. So like here's point 4, so 4 comma 3. If you want a second point. So x equal to 4, y equal to 3. So there's that line. But you don't necessarily have to have that. Just if it's helpful in you drawing the line. But then again, it might clutter up the picture here. So again, here's a function y equals f of x. And, these two functions are examples of functions that we often don't like too much because they have these breaks in them, often called non-continuous functions or discontinuous functions. Well, they're continuous everywhere except at that one spot. So maybe they're not that bad. Anyway, another graph of a piecewise function. 35. 37. Try 37. So fx is equal to x and x plus 1 when x is less than or equal to 0 if x is bigger than 0. So sketch the graph. Y equals f of x. So with this one, well, the line y equals x, that's the line whose y-intercept is at 0, so right at the origin. And there's a line of slope 1. So for x is less than 0, we have a line of slope 1 coming up to and ending at that point. So slope 1 is again 45 degrees, so maybe like that. All right, and you can put that arrow at the end if you want, or just probably should leave it out. And then, so that's for x is less than or equal to 0, and that's why we have the closed dot there. For x is bigger than 0, okay, we need to sketch the line y equals x plus 1. Well, again, that's the line of slope 1. But the y-intercept in that one is 1. So at x equal to 0, we get y equal to 1. Now, of course, if we pick x equal to 0, the value of f of x is taken by this piece. If x is equal to 0, then f of x is 0. Right? F of 0 is 0. But we need sort of an open dot as a indicator of where this piece's line is stopping. And that's at y equal to 1. Right, so open dot at y equal to 1. And then we have the line of slope 1 going forward again. So like that. All right, so y equals f of x. Again, this is the x-axis, that's the y-axis, and it has this discontinuity. So I asked you to hand in number 40, was it? Or was it number 38? Number 38, I believe.
38.
38. So in number 38, let's do one like that. And find a nice one like it. Well, there really isn't, to be honest. So here's something like 38. So f of x is equal to, and so it's got two lines switching at -1. So let's say x plus 1/2 x plus 5 if x is less than -2. And no, let's say just 3 there. And then
Bless you.
thank you. 2 minus x if x is bigger than or equal to -2. So with this one, the switch in pieces is happening at -2. Okay, so here's x equal to -2. So for x is less than -2, we use this line. And for x is bigger than -2, we use that line. At x equal to -2 itself, we use this one. So if x is equal to -2, then f of x is equal to 4. So that would be, say, up here. All right, that's y equal to 4. And this is x equal to -2 right here. Now, this line, again, needs a point that it's going to work up to and then stop. So at x equal to -2, the value of this expression is -1 plus 3, which is 2 itself. So right about there. So less than -2, we're using this line. So that's a line of slope positive 1/2 ending here. a slope of positive 1/2, right? Rise 1, run 2. So it's more of a flat line. It might be nice to find where that x-intercept is. The x-intercept is at -6. So 2, 4, 6. All right, so this is the line of slope positive 1/2, ending right there. And then after x equal to -2, we have the line of slope -1, starting here. So line of slope -1 with y-intercept 2. So looking like that. And the x-intercept of that is going to be at positive 2, of course. All right, so this is y equals f of x. So number 38, which is the one I asked you to hand in, it looks kind of a lot like that. Okay. For sure, on exam 2, I will ask you to sketch the graph of a piecewise function. Piecewise function where each piece is a line. So something like this. All right. The last thing I asked you in this section, well, the second question I asked to hand in 52. Let's take a look at 52. Oh, well, 52 is just a vertical line test. So, there's 4 parts on 52. Let's do 51. So, there's 4 parts in 51. And they're asking you for each curve shown, A, B, C, and D. Does that curve pass the vertical line test? So simple yes or no answer for each one. So this one, A looks like that. B looks like this. C looks like this. And D looks like this. Okay, so which curves pass the vertical? Actually, I didn't draw this one too well. This is better, maybe. Which one passes the vertical line test and which ones don't? So vertical line test means every vertical line intersects the graph at most 1 point. So this one,
A and C.
yeah. So yes, this one does. Yes, this one does. No, this one doesn't. Obviously, no, that one doesn't. Okay, so 52 just like that. Which ones pass the vertical line test and which one doesn't. In 52, the couple things you might notice, like in part B, the curve shown has got some sort of sharp corners to it. That doesn't matter. That doesn't affect whether it does or doesn't pass the vertical line test. Similarly, with discontinuities like this one, it doesn't matter whether it passes or it doesn't affect whether or not it passes the vertical line test. By the way, this is the graph of y equals 1 over x. Okay, in part C. So that's another standard graph. All right. Let's move on to section 2.3. And let's see if we can't do 2.4 as well. It's pretty short, these sections. So 2.3 is sort of a section about terminology on functions. If they say information about a function from its graph. Oh, and why are they asking about passing the vertical line test? By the way, in these types of these curves here, is because when you have a curve that passes the vertical line test, it is the graph of a function, right? Because for each x value, you get one y value for each x value above and below the graph. So in section 2.3, you'll be given a picture of the graph of a function. You don't necessarily know what the function is as an algebraic expression or anything like that, but the curves that you'll encounter all pass the vertical line test, so you know it's the graph of a function. So here's one such thing. So we'll say this is the point x equal to 3, y equal to 2. We'll say that's 4, 6, y equal to 6. And I guess this will be y equal to 3. If I can draw it straight. So x-axis, y-axis. So here is the graph of a function f of x. The graph of a function y equals f of x. Okay, from the graph, you can see what the domain is. Right, the domain is all of the x values that are vertically above or below the graph, right? These are all x values vertically above or below the curve. Y equals f of x. So in the example here, what would be the domain? Which x values do you get directly above, well, directly below the curve in this case, because the curve is always above the x-axis? What do we get in this case? Which x values? So the dotted lines here are just vertical lines to kind of help frame what's going on with that function. But what x values are we using here? Well, starting where? How about this x value? Are we using that? X equal to 1.5. Do we intersect the graph there with this vertical line through x equal to 1.5? Well, the answer is no. So with this one, we are starting from 3 and going forward. Right? When there's not a dot indicating a hard stop like there is here, right? Or you have an arrowhead that's just sort of saying, okay, well, it continues in that direction, or no arrowhead at all. Unless there's a dot indicating a hard stop, we mean that the function just continues as indicated. So here we're using all x's from 3 to plus infinity. So in the example above, so above the domain is plus 3, including that plus 3, all the way out to infinity. All right, so 3 less than or equal to x, just 3 less than or equal to x. Or x bigger than or equal to 3. The range of the function, which is all possible y values that the function attains, so the range of the function f of x is the set of all values that f of x attains. Right? So the x goes for domain values. The y's go for what are known as the range values. So in the graph y equals f of x, the range is all y values that are horizontally left and right from the curve y equals f of x. So example, so above, right, the range of f of x is, well, let's take a look. So which y values do you see obtained by the function y equals f of x? Right, so I mean, if you go straight left or right from the y-axis, so along horizontal lines, which y values do you pick up? Well, you pick up 2. You pick up 6, right about at that point. Right, so you go from 2 all the way to 6 up until that point. And then the function sort of slides along this line, y equals to 3, as it goes forward, as x goes out to plus infinity. Okay, so indicating that the curve isn't sort of bottoming out this way. It's just kind of sliding along until it almost becomes a horizontal line. So we obtain all y values from 2 to 6. Right? All y values from 2 to 6, and as we go out further, we don't pick up any new y values. So in the example above, let's smash that phone.
I think your screen stopped sharing.
It's because of the phone. The screen is as disgusted with the telephone as me. I'll fix it. Hold on. So here the range is from 2 to 6. All right, so you could just write it like this. 2 to 6. All right, so from the graph of a function, you can see domain and range. Let's look at a couple more examples of that. So here is a standard function that we will cover later. This is the graph of a function called the log of x, the logarithm of x. And it looks like that crosses the x-axis at 1. What does this picture indicate? Domain is what? Which x values are directly above and below that curve? From the way I've drawn it, what x values are vertically above or below this curve? Well, certainly no negative x values, right? Which positive ones? Well, all of them. All the positive values except x equal to, well, all the positive ones and not including x equal to 0. So here the domain is 0 to plus infinity. So x strictly bigger than 0. The range is going to be what? What y values are implied by this graph as being directly left or right? Sorry, did I say that right? What values on the y-axis are directly left or right from this graph?
All of them?
All of them, exactly. All real numbers. All right, so all real numbers, if you want to write it as an inequality, we just sometimes write this. Or like this. Whatever. I mean, other ways of writing it. All real numbers, so negative infinity to plus infinity. Another example from a standard function, that parabola. Is it still on my clipboard? Nope. So again, this is the graph y equals x squared, the standard parabola. So y equals x squared. Domain. So again, you have to sort of infer from the picture what's going on, because when your domain or range has infinite length, you're going off to infinity, you can't very well draw that. So you just have to imply it in some way. So, well, what's being implied with the range? I suppose that one's intuitively clear enough. So x is all right, exactly, and 0, and 0. So the domain is all real numbers. And the range is 0 to plus infinity, including the 0, right? So all x or all y bigger than or equal to 0. Okay. So domain and range, you can see it from the way a graph is drawn. Now, if you look at, for example, some of the problems in the section, they'll give you a picture of a graph with a hard stop left and right. So here's a final example. So if I drew this, so let's take this picture of the parabola again. And let's trim it down a little. So we'll say this is the point -1, 1, and this is the point 2, 4. All right, so I'm using the parabola as this function, as the graph of this function, y equals f of x, but only part of it. So they'll often indicate functions using hard stops like this. So with the stop either being a closed dot or an open dot. Fix my eraser. So in this case, we'll put a closed one here and an open one there. So in this type of example, the domain is -1 to 2, and the range is 0 to 4, not including the 4. Including the 0, but not including the 4. So -1 less than or equal to x less than 2, and 0 less than or equal to y strictly less than 4. Okay, so so typically a graph is thought of as continuing, continuing as indicated, like in this picture. So oftentimes people putting arrows on the left and on the right on the different ends of the curve, but you don't have to do that. If it stops, you want to indicate it stops with these kinds of dots as we've been using. All right, other important aspects of a function are what are known as relative maximums and relative minimums. Well, let's say intervals of increase and decrease first. So, given the graph of a function, let's go back to that original one I gave you here. So, notice that we've got this point up here. So we'll say, so this was the point 3, and we'll say then this is the point 6, I guess. From 3 to 6, okay, from 3 to 6, f of x is increasing. Right? So on the interval from 3 to 6, f of x gets larger, right? It's going uphill from left to right. And then from 6 to plus infinity, after that, it's going downhill. So we say f of x is decreasing. These are the intervals of increase and decrease for f of x. Now, when a function switches from increasing to decreasing, you get what's known as a relative maximum, so the top of some hump. When you switch the other way, from decreasing to increasing, then you get a relative minimum. So something like this. Let's draw another function. So we'll say this is -2, +3, and then this is on the y-axis, -2, I guess, and that's it. And then this, of course, is the origin, 0, x-axis, y-axis. So here is a function, y equals f of x. So the function is increasing on which intervals? The interval from negative infinity to negative 2. And on the interval from 0 to plus infinity. Right, so these are intervals of increase. And intervals of decrease is just one interval from negative 2 to 0. So we switch from increasing to decreasing at x equal to negative 2. So there is a relative minimum, at x equal to negative 2 with value y equal to positive 3. And there is a relative minimum right here did they say relative or local? Excuse me. Which term do they use? People either call it relative or they call it local. Local. Local minimum. Local maximum, excuse me. And there is a local minimum at x equal to 0 with value y equal to negative 2. Okay, so local maximums and minimums occur at domain value x. Right? They occur at the domain, I want to use the word value twice. Local maximums and local minimums are said to occur at an x coordinate, and they have a value given by the y coordinate. So this local maximum occurs at x equal to negative 2 with value 3. This local minimum occurs at x equal to 0 with value y equals negative 2. Okay, and where do local maximums and minimums occur? Well, they occur when you switch from increasing to decreasing and decreasing to increasing. Right? Increasing and then decreasing yields a local max. Decreasing to increasing yields a local minimum, as long as the function is defined at that point. Not that that's the total maximum value of the function. The function gets bigger than y equal to 3, like right over here. It just keeps climbing up to plus infinity. Similarly, it gets less than negative 2. It keeps climbing down or falling down like that. So the range of f of x is actually all real numbers. So with this function here, the domain and range are all real numbers. But, the fact that you have this hump topping out right here and another one bottoming out down there, those are important aspects of the graph. So we call those local maximums and local minimums. They're not absolute maximums and minimums. Just within some small portion of the function, that's a maximum. And within some small portion of the function, that's a minimum. Okay, what else was there in this section? Intervals of increase and decrease, local maximums and local minimums. And then one last thing that you can spot from a function to equations and inequalities. So when you have a function like this, it crosses the x-axis at a couple different points. So we'll say that this point is negative 4, I guess. And this point here is negative 1. And this point right here would be positive 2. So the solutions to the equation f of x equal to 0, right, are x equal to negative 4, negative 1, and 2. Right? These are exactly the points at which y equals f of x crosses the line y equal to 0, which is the x-axis. Oh, 10:56. So there's just a couple words left to say in this section here, but we'll finish that up tomorrow. But do get started on the discussion assignment, and we'll go over some problems for that tomorrow as well. Okay, so I have open office hours from 11:30 to 12:30 today in my WebEx room. I'll send you a link if you want to stop by. If you want to meet with me at a different time, then email me and we'll figure something out, okay? Have a nice afternoon.